Friday. We're doing it. Last day of January. It's crazy. Okay. Did I have any admin to say to you? Oh, yeah, I did. Haha, nice try, nice try. Just briefly. So today we're going to start chapter 4. I'm going to wrap up chapter 3 with this section 3.5 continuous distributions. It is really brief, but it'll just kind of lead us into chapter 4 and the normal distribution, which we've seen before and kind of talked about. And then I said, we'll talk more about that later. And here we are. So let's see here. Next week, we're going to keep working on the normal distribution, and I've just kind of built in a buffer day. So we might start binomial on the Wednesday if we have enough room, or when I say brief, I mean I'll say what it is and then we move on, right? And so just because it's not on the final exam or anything like that. And then dun dun, we got our test on February 12th. Hey, this didn't update. I updated this. Come on. That's what I wanted to show you. Okay. So we've got our test on the Wednesday, and then I release you. So we're not going to do a class. I'll post a video assignment. So it'll be a video by Zed Statistics, whom I really enjoy, and he does a really great job. And so he'll talk about some stuff, and then it'll kind of pause it and ask you a question, like an assignment question, and then play the rest of the video, and then it'll pause it, ask you some questions, you complete that, and then that'll be your class. It'll be on a distribution called the Poisson, which is fun, but I won't test it on the final exam. So this is all you'll see of it, and it'll just be kind of for completeness, but I will not test it on the final exam or a test. Hello? Let me just mute everyone. Okay. Wait, what? But I did. I muted, right? You guys saw me. Didn't I? Maybe they're trying to talk to me. I'm just gonna mute everyone again. There. Okay. So that's kind of the lay of the land.
Sorry, do you have chapter 4 notes posted?
Yep, all the slides are posted here.
Yes, you do. So sorry.
No worries.
Looking down.
There's one of these sections that I need to clean up, but I think it's chapter 7, so I think I still have some time. Today, you get a new piece of free paper. Good thing I brought this many, huh? Thanks. I posted the tables that I'm handing out. Just some of these are hidden, but under course material, you'll have the tables, but you guys get some snazzy printouts. But if you want the PDF, it's on there too. It's just kind of nice for when we're talking about it. Let's all have your formula sheets. Or maybe you want a fresh sheet. That's allowed.
Oh, actually, there is somewhere. There it is. I've just been writing down the formulas basically every time we show one, and then I just rewrite it in my notes.
I mean, that's good. It's good to be familiar with them. Okay, so the tables that I just handed out look like this, and there will be 2 sets of tables. And so the one I just handed out is called the Z table, and that'll become clear why later on today. But it's 2 pages, and then later we'll introduce the T table, just if you're trying to sift through the tables that have been posted. So, like I said, I want to finish chapter 3. I really hope I did kind of tie up pretty quickly, I guess, last day. But I did you guys see, I added in the solutions to this one after class before I posted the notes. So there's another example to do that you could try. But we're moving on. Starting fresh today. Well, sort of. Finishing chapter 3. So continuous distributions. So last day we talked about probability distributions, weighted means, how do we find the variance of those, right? And so let's say we have a histogram of the distribution of heights of US adults. Okay. The proportion, now I want you to kind of start paying attention to the proportion. The proportion is a probability. So usually the chapter we just finished, we call it probability, and that's the chapter that no one likes. It's hard, right? Tree diagrams, conditional probabilities, ugh. But now we're done with that. And so, but it gets confusing because we're going to have to deal with probabilities throughout the course, but not in that way. So that section is called probability. And of course, we need probability knowledge, but it'll be different. Okay? And so a proportion is a probability. And if you multiply it by 100, you get a percentage. Okay? So I'll do a roughly equals. Notice that these are the 3 P's, and you kind of can use them interchangeably as we've seen already. Now, what's important is that all of these, well, the proportion and the probability is going to be an area under the curve. Area under the curve. Which, if you've taken calculus 2, you're thinking, oh my gosh, we have to integrate that? No, we don't. That's what the table does. So we don't have to do any calculus. It's happening in the background. But for us, right, areas under the curve is integration, but we're not going to do that. So the proportion of data that falls in these shaded bins, you could do some problem solving if you knew the heights of all these bins, which I've not given you on purpose because we're not actually going to do it. But if you had to figure out, okay, what proportion of this area is shaded, right? In fact, it's the proportion between 180 centimeters and 185 centimeters. You can find areas of rectangles, right? That's perfectly doable, right? And so, and if you have these 2 rectangles, you can find those areas individually, and then you can add them up, and then there you go, right? But that seems like a lot of work, and it is, but that's the idea. And so the proportion of data between 180 and 185 centimeters will translate to the probability of someone, a randomly selected individual, being between 180 and 185 centimeters. So this area will be the probability, or sorry, the proportion, or the area, will be the probability that a randomly selected adult, US adult, I guess, is between 180 and 185 centimeters. And so that's how we're going to talk about probabilities from here on out. Okay, fine. We'll dip into binomial, and then that's how we're going to talk about probabilities. But I think you're going to like the binomial. Say no more. So what we can do, since height is continuous, what we usually do is we kind of smooth these bars out. Okay? And so it's called the probability density function. I'm not going to call it that ever. It is. And it's more if you're kind of Googling things, then just recognize that this smooth curve is the probability density function. And so, hey, I already said this. But the probability that a randomly sampled US adult is between 180 and 185 centimeters is this shaded area under the curve. Notice how we've kind of smoothed out the curve. And for us, we're going to have an even smoother curve with the normal distribution. Whee! Okay, not my best normal distribution, but not my worst. Right? And so, and you can tell that that's where this shape is headed. Okay. Continuous probabilities. So if you had to find the area under the curve here, but just at 180, how do you find the area of a rectangle? You take the width times the height. What if you want the probability at 180, right? The probability at 180 would have a width from 180 to 180, a width of 0, which means the area is technically 0, right? 0 times any height, it doesn't matter. And so, so what's kind of mind-boggling is that the probability at any one particular point, right? So an exact value on a continuous scale is 0. We see that there are probabilities, right? But you have to go between two values to make an area. Okay. And so to me, that's just kind of like, whoa, that's weird. Because you can be between 180.1 and 180.2, sure, but then you've made a little bit of area there. And there's some probability of that happening. But at exactly 180, no more, no less, it's 0. So with that, we're getting into, wow, I wrote this sloppy. Okay, let me clean this up. Chapter 4, which is distributions of random variables. We talk a lot about random variables, but the normal distribution is also a random variable, unlike last day, right? That was a discrete random variable that we talked about. But the normal distribution, remember, was, let's see if I can do this, pull it off. Nice. The normal distribution looks like this. It's this bell shape, right? And what we know, right, is if we have a normal distribution, the mean and the standard deviation are the most appropriate measures of center and spread. Too fun over there. The mean and standard deviation are the appropriate measures of center and spread. And we said, okay, well, the normal distribution is going to be centered on the mean. In fact, we're going to center it on the population mean. Yeah. And it's symmetric about the mean. In fact, it's unimodal, right? There's only one mode. And so I'll add that here. Unimodal and symmetric about the mean, which is on the next slide, but I wanna say it myself. Okay, so today we're gonna learn about all the properties of the normal distribution, but kind of a spoiler alert, but also something to keep in mind as we go through this. The reason we use the normal distribution is because here, just as we saw earlier, the areas under the curve are probabilities. The area under the curve, oops. Is a probability, are probabilities? I'll stick to singular, I guess. Knowing that, and knowing what you know about probabilities, what's the total area under the curve? Has to be 1, right? And so then this tells me the total area under the curve is 1. That's still true. Okay. And we're going to leverage that fact a lot, right? Trying to find areas that we need to satisfy some question. So what's more is that these tails, and I'm getting ahead of myself, but these tails keep going to negative infinity, positive infinity, and they never, ever, ever close on the axis, which again is a kind of mind-boggling to me, because how can you go to infinity and never close the tail but still have an area of 1 under the curve? Calculus says it's so, but it's just kind of a weird mind exercise. Yeah. So that's something to keep in mind. And what does that mean? It means that there's always a probability of something happening, right? And so it's really just allowing for an infinite number of outcomes on a continuous scale. Okay, nice. So like we said, the normal distribution is unimodal and symmetric, and it's got a bell-shaped curve. Okay. And the reason we kind of call it normal, I use it as a name, but it's also, that's just to kind of guide you towards it being a name, and it doesn't really mean anything, but a lot of things are nearly normal. Like we saw with that heights of the US adults graph, it looked kind of like, if you squint, you could call it normal, right? And so a lot of things are nearly normal, but none are exactly normal. Okay? And that's okay. We're going to approximate it with a normal distribution. Some notation that we use is this little guy. And usually what we do is we say that x, some random variable x, random variable x. For example, it could be the heights of US adults, for example. Or maybe I should say example. Can I just say heights? For example, heights, right? X is just a placeholder for anything that we know varies across populations, right? Which is pretty much everything, right? Even if you look at something that's really, really uniform, right? If we had a measurement or a measuring device that was very, very precise, if we look at the heights of these chairs, do you think that they're all exactly the same? No. Roughly, right? But we expect some of them to be shorter than others and some of them to be taller, but most of them hovering around the average. And so we can have really, really tight normal distributions. In this case, right, the heights of the chairs, they're basically the same. Or we can have really, really wide normal distributions. And so here we can call it the height of the chairs if you want, right? And we use this little, and I should make it, it's a tilde or a simulates, but you're gonna read it as follows. It's a tilde, but tilde. But we're gonna read it as follows. Follows a normal distribution, which we denote with a capital N. Right? And then so the next thing here is a normal distribution. Do you remember how we fully described a distribution? We had to talk about the shape, and now we're focusing on the normal shape. And so this part tells me the shape, right? Or this part tells me the shape. And then I had to communicate the center, and I had to communicate the spread, right? So this is just a shorthand version of communicating what this distribution looks like. And so here, so the N is kind of bumped up and then it's got the brackets right next to it, mu sigma. A normal distribution with, and I'm gonna need more room here, with mean mu and standard deviation sigma. So this becomes kind of our shape, center, spread, shorthand, right? That's going to be way shorter than me saying, oh, it looks like it has an approximately normal distribution centered on 20 with a standard deviation of 2, right? That's a long sentence. You're allowed to write that out if you want, but I will be using this shorthand notation, and you're expected to be able to read it. You don't have to necessarily convert things to it if you don't want to, okay? But you do have to be able to read it. And so what this means is we have a center here of mu, some generic mu, and there's not yet any place to put the sigma. And so usually I just kind of plop the sigma down here somewhere, right? I want to have an idea of the spread, but there's no obvious place yet to put the sigma. And in fact, you're just going to kind of float, float sigma below the mean somewhere, below the mu, for reference. We're going to do calculations with these values. And so that's why you want to have it kind of in your periphery, if you will, right? Where, okay, you've got this normal distribution centered on some mean, and then you'll need the spread for your calculations. So you just kind of jot it down somewhere. Okay. Any questions so far? Okay. So this one, it's kind of a cute example, but it doesn't really say what I want it to say. So, but it is kind of a funny example about heights. And does OkCupid still exist? Who knows? so many dating websites. Anyways, they analyze the heights of people, but let's talk about what I need to talk about. So these, the mu and the sigma. So if I have a normal distribution with a generic mean mu and a standard deviation sigma, that mu and sigma, they're called parameters, right? Parameters we introduced as measurements from the population. These are parameters, which are measurements from the population. It's too bad that we didn't do the normal distribution immediately after we introduced all these terms. I think it would kind of tie it together, but now we have to dust it off, and that's okay. We can do it. If you don't know anything, and if you kind of ignore the scale for a bit here, let's see what I can do. Temporarily. Those two things look the same to me, right? It's just the center and the spread are different. Ta-da. And so here we have a center, and maybe I'll zoom in again. A center, boy, not like that, at 0 versus a center at 19, right? But as far as we can tell, the center has just been shifted over to 19. So this, whatever this is measuring, it has an average of 19, and we're expecting some variability around that. Okay. Now, that variability is the spread, right? And so here, if we have a look at where we kind of, and we already mentioned, I gave it away, that these tails keep going forever, right, to infinity. And so, but if we consider this distance, this is, if the standard deviation is 1, then this is going to be 3 standard deviations, right? So this is a distance of 3. Equals 3 sigma, 3 standard deviations. Whereas, I guess I'll need my calculator. I know, embarrassing. What if we do the same thing for the other one? We kind of lose interest. The area below the curve after 3 or 31 in this case, right, is so small. Areas under the curve are probabilities. So it can happen, but it's very unlikely is what that translates to. Now that distance between 19 and 31 is 12. This is a distance of 12. But wait, there's more. In terms of how many standard deviations, that is, if I divide it by 4, I get 3 standard deviations. And so again, I get 3 standard deviations. And that is a fact. Okay. So on either side of the mean, we typically are only able to move out 3 standard deviations before the area becomes so small, or the probability becomes so small. So what this translates to is the area under the curve past mu plus 3 sigma, and also on the lower end, mu minus 3 sigma, whatever the sigma is, right? It doesn't matter what the spread is, it has the same property. Yeah. And so the area under the curve past mu plus 3 sigma is very small. It exists, it's not 0. I'll do that in red. Not 0. And that's the reason a statistician is never, ever, ever going to tell you that a probability of something happening is 0, because there's always a probability of something happening, right? And so if we put these histograms or distributions on the same scale, they would look like this, right? So here's the one centered on 0 with a standard deviation of 1, nice and tight, okay? And here's the one centered on 19 with a standard deviation of 4, right? Kind of spreads out. And so that's what they look like. But in general, they have the same anatomy, right? You can move out 3 standard deviations in either direction before it starts becoming very unlikely. Possible, but unlikely. Right. Okay. So how do we use this? I'm not, beyond doing this question every term, I'm not very familiar with the SAT scores and the ACT scores. So I don't know, just, you don't have to be, clearly. But SAT scores are distributed nearly normally with a mean of 1,500 and a standard deviation of 300. ACT scores are distributed nearly normally with a mean of 21 and a standard deviation of 5. Now, knowing the means, just looking at those means, would you want to, so if your university is just looking at the raw scores of your SATs and your ACTs and comparing them, that's a concern, right? You'd be kind of concerned you can't compare them. One is centered on 21 and the other one is centered on 1,500, right? 1,500. And so to be able to compare these two from 2 normal distributions, what we do is we standardize them. Okay? And so what we're going to talk about is, okay, relative to the SAT distribution centered on 1,500 with a standard deviation of 300, how many standard deviations was this score from 1,500? Right? And then we can do the same thing with ACT scores, right? How many standard deviations was the score from the mean, right? And so that's what we're going to leverage. And so we've got this cute example, subtle, but a college admissions officer wants to determine which of the 2 applicants scored better on their standardized test with respect to the other test takers. Pam, who earned an 1,800 on her SAT, or Jim, who scored a 24 on his ACTs. So these are just standardized tests that you can take in the States, and they are used for college applications and just kind of to determine how smart you are, I guess. Or how well you would belong at a specific institution. Here we have our SAT scores. I'm just going to label that down here. And Jim, so Pam wrote the SAT and Jim wrote the ACT. It doesn't matter. You can use them both. I wonder if people write both. Does anyone know? I don't know. Too stressful, maybe. We're told that the SATs, just practicing our notation, follows a, right, little tilde, normal distribution with a mean of 1,500 and a standard deviation of 300. And we were told that the ACTs, and maybe I'll move this up here. Whee. The ACTs also followed a nearly normal distribution, but they were only centered on 21 with a mean or a standard deviation of 5. So to compare these scores, what we said is we're going to translate it to how many standard deviations above the mean did they score, right? It looks to me like if this is, oh, and there is a very, very faint line here. I'll just fill it in because it's nice to see it. I'll use red for this one. So they both scored above the mean, right? We can see from the graph that maybe Jim didn't score as well as Pam relative to his own distribution, right? But we want to have kind of concrete evidence of that. And so to compare scores, from the two distributions, we need to figure out how many standard deviations they each scored from their respective mean. Whoa, that's a lot of words. We need to figure out how many standard deviations each scored above their respective mean. Yeah, go for it. Yeah. Is it up front here or? How's that? Yeah. Wakey, wakey. If you had to problem solve this, let's focus on, and I'm gonna add a page here. Wait. Oh boy, where are my lines? Lines. Good. Let's focus on, whoops, Pam. It's gonna look weird, but that's okay. Let's just paste it. Pam scored, we were told 1800, I think. Let me confirm. Pam scored 1800 on her SATs. How many standard deviations above the mean did she score? The SATs, we know, follow a normal distribution centered on 1500 with a standard deviation of 300. You could do what? You could find this distance, right? And then divide it by 300, which is exactly what we're gonna do, right? But even if you didn't have formulas and things, you would get there, right? If you kind of remembered that the overall goal is to find how many standard deviations it was, right? Then we can compare the number of standard deviations, right? And that's going to be standardized. And so what we want is we're gonna say the distance between the mean and the score divided by whatever the standard deviation is. I'm going to introduce just kind of some standardized notation that we'll be using. And so to find this distance, we're going to take the score minus mu. Okay. So in this case, the thing that I'm interested in, right, and then subtract it from the mean, or sorry, subtract the mean from it. words. And then divide by sigma. That's going to translate to the distance. And what's nice is by taking the score and then subtracting the mean, here I have a score above the mean, 1800. If I subtract 1500, I get a positive value. We kind of flip the script and say someone got 900, and that's my score. Then 900 minus 1500, which is above, would generate a negative value, right? And so the positive and the negatives, if we stick to this calculation for the distance, will also tell us if we're above or below the mean, right? And so that's nice. And so that's why we use it as a standardized calculation. And so if we have the score minus mu over sigma, this is going to be the value we are interested in. Oops. Well, this doesn't really read well, does it? Interested in. Later, it's going to be the value that I want to find a probability associated with. And so here, oh, that's what I wanted to say, make a note about too. In terms of the distance, if we use the score minus mu, we get a positive value for scores above the mean. And negative values I don't know why I'm not writing over here, but that's okay. For scores below the mean. All right, so it's telling. So for us, if we take the score minus the mean and divide it by sigma, I get her score of 1800 minus 1500 divided by 300. Bust out your calculator. Don't do it in your head. 300, well, maybe 300 divided by 300 you can do. I get a 1. So 300, keep that up. So that tells me that Pam scored 1 standard deviation above the mean. Therefore, Pam scored 1 standard deviation above the mean. That's great. How does that compare to Jim? Let's see. Jim scored 24 on his ACTs. And they're centered on 21 with a standard deviation of 5. Uh-oh, it doesn't look good for him, does it? So for Jim, oops. Jim scored 24 on the ACTs, which follow a normal distribution centered on 21 with a standard deviation of 5. Just kind of jotting down so I don't have to scroll up and down so much. Which means that his score, oops, minus his mean divided by his sigma is 24 minus 21, still above the mean. Close. 24 minus 21, it's 3 divided by 5, but no cigar. 0.60 if you want. ha. Pam scored better, right? Did better relative to her group of test takers. And so therefore, Pam's score is better than Jim's. So this idea of converting, right, from any normal distribution, and the only thing is that you have to have a normal-ish looking distribution to do it, but then what you can do is you can take from any mean and any standard deviation, and you can always standardize these values to compare them, and then we'll standardize to be able to find probabilities more easily. Right? And so this is what we call a Z-score. So when we take the score minus mu over sigma, we could, if you want, label that a Z. Right? And I guess it's confusing because they got a score on their test, which is different from the Z scores, but not that different. In general, or more simply, we have Z is X minus mu over sigma, where X is just a placeholder for the thing that you're interested in, right? The thing you want to standardize or find probabilities associated with. And so here, where X is the value of interest, squeezing a lot on these slides. So, okay, nice. So the Z scores are what we're going to use a lot for the normal distribution, right? In fact, you already have the table, called the Z table. Which is how we're going to find probabilities associated with a Z. Oh yeah, we already talked about this, so we did the math, we got there, problem solved, right? And then the nice part is that once we've standardized, then we get this, I think of it as kind of a mini version of a normal distribution. It's just shrunk down, right? But the shape of the SAT scores and the ACT scores aren't going to change just by dividing them by the standard deviations, right? But what's going to happen is that Z, or these standardized values, follow a normal distribution still, right? Just a shrunk down version, centered on 0. That's a fact. Why is it centered on 0? Because the mean is how many standard deviations from the mean? 0, right? And so it's just shrunk down and it's centered on 0. Now, if I put 3 and -3 on here, if you had to guess, what's your standard deviation? If we can always fit 3 standard deviations until we kind of run out of space, it keeps going, but until we kind of run out of space, then I would say my sigma here is 1. And that's true. Oops, I'll do just 1. So that's nice. So then we've shrunk things down, and by standardizing, I mean calculating this Z score. Yeah. And so Z is the standardized values, and Z follows a normal distribution. centered on 0 with a standard deviation of 1. And that's just a fact. So we developed it on our own. Did it all by ourselves. Right, the standardized values, we took the observation minus the mean over the standard deviation. In fact, I already introduced the formula, which is on your formula sheet. In the next section on your formula sheet, I know, who knew that we were already making our way downtown? No, making our way through this formula sheet today. If X follows a normal distribution, now you can read this. Right, it's not too bad. It follows a normal distribution with a mean of mu and a standard deviation of sigma. Then you can use, it has to be normal, right? And you have to know the mean and the standard deviation. Then you can use Z, which follows a normal distribution centered on 0 with a standard deviation of 1, where Z is X minus mu over sigma. And you don't even really need this one. I'll show you why, but I think it's going to take us till next week. So. Right. Okay, fine. Why don't you need it? Can you take this little guy and solve for X? What would you do? You'd have to multiply Z by sigma and add mu. Well, ta-da. So some people like lots of formulas. I like as few formulas as I can. Right? I can do my own work. But it's on there in case you prefer it. Okay. But later, like I said, probably not until next week, but something to look forward to, right? X minus mu over sigma. Yeah. The thing is, you can always calculate Z-scores because you can always calculate the mean and you can always calculate the standard deviation. They're only appropriate measures of center and spread if you have a normal distribution, but you're always able to calculate Z-scores, right? Because you can always find the mean and you can always find the standard deviation, right? And so only when the distribution is normal can we use the Z-scores to calculate percentiles. And then when you see percentiles, you're probably thinking percent, but then you're thinking, well, a percent is just a probability, which is just a proportion, which is an area under the curve. I know, maybe not, but you will. Okay. And so really, the percentiles are just a special case of areas under the curve. We've seen percentiles before. When? When we did our quartiles, right? Those were percentiles. And so we can still find our quartiles, and our median was a percentile, right? The 50th percentile. And so we've already talked about percentiles, and dang it, they're going to come back to haunt us, right? As a rule, this is a rule. Observations that are more than generally 2 standard deviations away from the mean, right, in either direction, okay, are usually considered unusual. Usually considered unusual, right? And so that's when we start kind of reacting and saying, well, that's kind of a weird observation, okay? And so we use the absolute value. Do you guys remember the absolute value? Just drops the negative. Does a little bit more, but essentially for us, effectively, it just drops the negative if it's negative. And then if the Z itself is greater than 2, we consider it unusual, right? So in terms of our curve, we're going to start to have our Z centered on 0, and I'll start writing kind of sigma down here. So we're gonna need it to calculate some things, right? But here I've got my Zs. So these are Zs on a number line, right? And maybe I won't write Z here. Maybe I'll do kind of highlight this way. Here Z equals 1. Here Z equals 2. And here Z equals 3. Here Z equals -1. Z equals -2. And Z equals -3. So we get this threshold. It's an approximate threshold. But just as kind of a developing some gut reactions, right? Whoa, I got a Z larger than 2. We know Z continues to infinity in either direction still, right? And so that's true for any Z goes to, I'll use the arrow for goes to infinity, and then here Z goes to -infinity. There's a problem in the assignment where you usually get a Z, they're all randomized, but the Zs are set to be, I think, 13 or something. And I always get lots of questions about that one. But how can that be? That can't be. Well, it can actually. Not just 13, but it can go to infinity, right? And so just remember that. It's okay if you come across that one. But what does this do? This gives us some threshold of saying, okay, that's kind of unlikely, right? And so the example that I like to use is sometimes we have intuitive knowledge about spread, right? So let's say we're talking about the lengths of mosquitoes, right? If you kind of imagine all the mosquitoes, you know they're not all exactly the same length, but you know they're approximately, well, maybe I'm like doing a killer mosquito here, but around these parts, they're not very big, right? And we know there's some bigger ones, some smaller ones, right? But if I told you, hey, I found a mosquito and it was 1 centimeter longer than the average mosquito, you would say, oh no, I hope you squashed it, because that's terrible, right? What does that translate to? You might have a center of, I don't know, 1 centimeter with a standard deviation of 0.1 centimeters or something really, really tiny, right? And so then when I say, okay, I went 10 standard deviations above, yikes, right? So that's kind of where your gut takes you, right? Whereas if we think about dogs, right? Dogs, there's all different kinds of dogs. And if we talk about the length of a dog, right? There's some average length of a dog, right? And if I tell you, you won't believe it, but I found a dog that was 1 centimeter longer than the average dog. You'd say, oh, okay, congratulations. That's not important to me. And so what that translates to is that's just hanging around here, right? Kind of where you're expecting things to be, right? And so we have this kind of built-in intuitive knowledge about spread for a lot of things, but for a lot of our data, we won't, right? So that's when we need to rely on Z-scores, right? And so just in general, if you're more than 2 Z-scores away from the mean, you start to get that queasy feeling. No, but you start to wonder, that seems weird. Are you sure it was a mosquito? Maybe it was some other thing, right? And so that's what we're kind of building towards. So my rant leads us to percentiles. Well, there was no segue. Percentiles, here we go. We already said that the area under the curve is a probability, right? And a probability is a proportion, which is a percentage. And so a percentile is going to be the percentage of observations that fall below a given data point. Okay? And so if we're thinking about, this looks like Pam's SAT scores, right? She would be scoring at some percentile, right? And so here, the area, this shaded area, represents the percentile Pam scored at. Which is also important, right? A lot of exams, you have to score in the 90th percentile, for example, right? Which would force, let's say here, right, at some score down here, we can force this area, and I'm going beyond, to be 90%, right? And so we can work it both ways, right? We can take a score and I can find what percentile it's scored at, or I can force the percentile to be 90%, right? 90% below it, 10% above it, right? And then you have to score higher than that, right? If you've done any sort of, or looked into rather maybe, any sort of professional exams, you usually have to score in the 10th percent or the 90th percentile. I did it. My own biggest pet peeve. 10th percentile, that's easy. You just have to be better than 10% of the other test takers. 90th, not so much, right? That means you have 10% above, right? And so 10% above. So those are the two different types of questions that we're going to work towards solving, right? Notice that, okay, so here I have a score and I want to find what percentile she was at, versus I force a percentile and I want to figure out what score makes that happen. Yeah. Okay. Calculating percentiles. In real life, I'll do this first. We're not using R, we're using Excel. It's pretty common to use R. R is a statistical programming language. And if you want to learn it, I am happy to help you, but we're using Excel. Okay. So just in general, any sort of software, right? Like I was saying, in real life, you would just be using software for these probabilities. And so these percentiles are really going to translate to probabilities or areas under the curve. Maybe I'll clean that up. They're the same. Probabilities are areas under the curve. So using software, it's really just got a fancy mechanism to generate these values, or rather kind of a better mechanism. And so just for some background, these tables are really archaic, right? You don't want to tell your boss that you're using your Z table. Unless they're really old, then they would be impressed. But you should probably use software. It's just that we use these tables for tests and just kind of, closed book. I tried to get this course to be kind of in-class online assessment so that you could use software, so it was more real. But then other people didn't like that. So here we are using tables. Me printing, hate paper. Anyways, so that's my rant. But we should use software. And so that's why you've got your Excel assignments to kind of help you along. And for some of these, I will bring in Excel. This is when I'll start trying to incorporate Excel. It's just a little bit difficult on my iPad because I don't have a keypad, so makes it kind of weird. But sometimes I have some pre-baked things. Okay. And so in Excel, you'll be able to use one of the commands, I think, is norm.s.dist. And don't worry, there's an Excel assignment coming up on just this. No, make it stop. You'll get a break over reading break. How about that? Well, besides the one. And it's going to take a Z and just always cumulative equals true. Cumulative, right, we understand it in terms of final exams. The final exam is cumulative. That means that everything up to the final exam is covered on the final exam, right? And so same thing, right? I guess maybe I didn't want to scratch this guy out, right? Because what we're going to be able to do is we want to find all this area cumulative up to some Z. There. There are fancier ways where you can just give it your score and the mean and the standard deviation, and then it calculates the Z for you, and then it gives you the probability. Okay. In general, it always gives you the area to the left. Same with the table. Okay. And so this returns, I really scratched this thing out, but I probably shouldn't have. Returns the area to the left of Z, right? Whatever Z you gave it here. So you can calculate your Z, and then, but I do want to have this kind of scratched out here.
Does the true just mean the standard deviation?
So the true is technically cumulative equals true. If you said false, it would return 0. And that's going back to, well, if you've got a continuous scale and you're just looking at a distance of 0 for the height of this, or for this area, right? Then you get no area, right? If you've gone a distance of 0. And so it's always true for the normal distribution. Yeah. So up to and including Z, which means the area up to and including Z from the left. Should add that. Technically from negative infinity, but let's just say from the left. There are other distributions where you'll be able to kind of switch between cumulative equals true and cumulative equals false, because they'll have probabilities at that point. But for the normal distribution, it's always just true. Okay. Good. We're doing great. So here is a version of the table that you have. Maybe what I'll do is I'll grab our table instead, because I like it better. That's why I use it. I'm going to copy this. Oh, whoops. I need to grab both of these. Copy. Paste. Yeah. So these all look the same, to me. But this is the one that we have. So here, this is our Z table. Oops. So this is the one. It didn't print with the lines, but for the test, because it helps your eyes kind of focus, I'll make sure that it prints with the kind of shaded areas. Because if you just look at this, what a mess, right? So how do we read this thing? Well, some key things first. We've got our Z. Let's start there, making it a Z table. Now our Z is starting here, -3.4, and going all the way down by 1 decimal place until we get to -0.0. Yeah. Are you on the positive side? So there's a negative side. I was just gonna say that though. So here you have your negative Zs. Whoa, what can I? Right. And then on the next page, you've got your positive Z. In the left-hand column, you're gonna have the whole number of Z as well as the first decimal place. And so here, this is can I do it here? The whole value of Z and the first decimal place. We're going to be able to handle two decimal places. Hold up one finger. By incorporating the second decimal place up here. So here, this is the second decimal place. Of Z. Which means in your work, we always round Z to 2 decimal places. And so if we're using the Z table, therefore, in our work, we always round Z. You have to round properly to 2 decimal places. It's going to take the whole page here. If using the Z table. As foreshadowing, we are going to be migrating towards using the T table later, which confusingly has 3 decimal places. And so that's why I added the caveat if using the Z table. But for now and for test 1, we're just using the Z table. So that's a good rule to have. Okay, so what is this this mess? All this mess here. This is going to be the probabilities, right? And so here, what color haven't I used? Oh boy, kind of ran out of colors. Purple. These, we call them table entries. Which are probabilities. Oops. Or areas to the left of Z. It's always going to be areas to the left. And the reason I like this table is because it's got this little guide. And if you learn to embrace it and don't just ignore it, it can kind of help remind you of what the table is giving you, right? And so here, we said that the table entry is the area under the curve, right? Or the probability to the left of the Z that you gave it. Okay. And it's even got this description here. The table entry for Z is the area under the standard normal curve to the left of Z, right? And so I know it feels like, just give me less, but here it's there. It's telling you exactly what the table is doing. I know it doesn't feel like it right now, but let's have a look at this thing. So what I want to do is, oh boy, I really marked this up, didn't I? Okay, before I do, I want to switch to the positive Z side. Remembering that, okay, we get a negative if we're below the mean, and we get a positive value for Z if we're above the mean, right? If you have a Z of 0, what do you expect the area to the left to be? It's symmetric about the mean, and the total area is 1, so I'm going to go with 0.5, right? And so, and that is exactly what we get if you plug in a Z of 0.00 is 0.5, right? So it's the value that splits the table in half. And so it just kind of moves over to the positive side on the flip side. And what happens is now that we're in the positive Zs, right, all these areas, and these are all areas under the curve to the left, right, should all be greater than 0.5, right? And so it looks like hodgepodge, but there is rhyme and reason here. And so let's have a look here, noticing that it's still the area to the left, right? But now I'm above the mean, so I'm going to get a bigger area. What if you need the area to the right? The area to the right, you use the fact that the total area is 1, right? And so I'll add that here. Oops. Where? If we need the area to the right, we use the fact that the total area is 1. We use the fact that the total area is 1. And usually how I denote it is I draw a line up to a point and then I draw a little arrow, because shading it in, there's going to be a lot of overlaps pretty soon. And so then what I say, so then I use this arrow up above, because then I'll be able to incorporate more areas like this, right? And so I'll remove that for cleanliness. But here, then this area is 1 minus the area to the left. So if we go back up to the negative side, and maybe I'll go in and grab a fresh copy that I haven't marked up here. I'll do this. So if we focus on this part of the negative table, it's just a continuation, right? So we're on a continuous scale. So Z is on a continuous scale, bless you. And Z is on a continuous scale down here. And we know that Z is centered on 0. Let's do this. Z is centered on 0. I should move this Z. Oh, you know what? let's use a more, no one-trick pony. Pink means it's important, or I just want it to stand out. So here I'm on my scale of Zs, right? This high peak means that the probability of these Zs is quite high, right? Whereas if the area under the curve is small, the area under the curve is the probability, which means that the probability of these Zs is small, right? And so this table, they stopped. What's the smallest possible value that we can find on here? Well, it's negative 3.49, right? And so at some point, some poor soul decided, you know what? I don't want to do all this math every single time. How about I just do it once and for all, and I make a table and I share it with my friends, and they'll all be so happy. Right? And so the table was born. But there's a lot of math that goes into the background here, and so it's a lot of work, and it would be tedious if we didn't have computers, right? And so they decided, nah, negative 3.49, I'm not going to go any further. Why? Because how we read this table is if Z is negative 3.49, the area to the left is 0.0002, right? I don't think we need to get any smaller than that. We know it keeps going, right? But from a Z of negative 3.49 and negative infinity, that total area is 0.0002. There's no point in continuing. So here, how I draw this, right, is my little arrow going out this way, and it's 0.0002. That's a probability. You can multiply that by 100. Let's try it. 0.0002 times 100, and I get, or 0.02%. Right. Still very, very small. Who cares? After that point, you can say the probability of that is approximately 0. You can't say it's 0 because it's just less than 0.0002. You don't know how much, right? You'd use software for that. Yeah. And so you want to be really careful. It keeps going, but we stopped recording once we hit 0.0002. So then, if you do negative 3.48, where would negative 3.48 fall on this Z number line? Well, it would fall just beside it. How about for kind of readability, I move in a little bit, and let's do negative 3.4 or 0.04, I guess, just for fun. And so here, let me use a different color. If I have a Z of negative 3.04, then this table tells me that the area to the left of that is 0.0012. Still really small. Probably shouldn't have put it so close to the middle. But anyways, it's just for visualizing these things. And so then you might be interested in, okay, well, we said 2 was kind of a cutoff point, right? A Z of 2. So how about we go back to our table and find the area to the left of a Z of negative 2? We'll do it even here. a Z of negative 2.00. And you'll want to be careful when you're using this table, especially for homework and for just kind of the tests and stuff. Then I like to kind of gently fold it gently. You can do whatever you want, actually. You can do it hard, but I like to fold it over and just kind of use it as a ruler. Otherwise, it's really hard to see. And so, I don't know, any straight edge will do, right? But you don't want to, it's really easy for your eyes to jump around on there, right? And so I use the highlighter on here, and you're welcome to use the highlighter, but there's going to be a lot of them that you're doing, so it might get confusing. And so here, from this table, from negative 2.00, I have an area to the left of 0.0228. Oops, I wanted this. All these purple. Can I move this over? I got a little, oops, maybe I just delete it. I got a little ahead of myself here. Let's put it here. Otherwise, it looks like it's really close to the center and it's not. Like I said, these are just to help us visualize what's going on. But now I can put negative 2.00. And I've completely forgotten what the area was, but I think 0.0228. Which means that if we use 2 as an approximate guide, then the probability of being below that point or more extreme, right? More extreme in this case is into the negative tail, is 2.28%. That's relatively low, right? And so that's why we use the 2 as a threshold. And so here, we've seen, I was gonna say, we have seen probability notation. Uh-oh. You don't have to, you can write it out in words if you want to. I think what you'll find is you get really annoyed with writing out the words and then you start adopting the notation. And so again, I just need you to be able to understand it. And then you can start to apply it if you want to. You can write it out in words. The probability that Z, so far so good, I think, is less than or equal to negative 2.20 or 2.00 is 0.0228 or 2.28%. Let's write out how we read this. Read this as the probability that Z is less than or equal to negative 2.00 is 0.0228. I guess it goes to the there. All right. If you prefer to write that, that's cool. But for shorthand, I think it might be nice to use the probability notation. As an example, what is the probability that Z is greater than or equal to negative 2.00. We use the equal to in both scenarios. You don't have to do anything to account for that. Just kind of flip it. Because at -2, we said the probability of that is 0, exactly. So it doesn't matter. So now, if I'm asking what's the probability that z is greater than -2, then you can sketch it out and you can say, I've got my 0 here, I've got my z is negative 2.00. I already found that this area is 0.0228. If you want to shade it, right, this is the only probability that we have on here, so you can shade it. But what we want to find is this area, right? Or from this point, I want to move all the way over here. That's going to be 1 minus 0.0228, which is 0.9772. Okay. Good. I think we're ready for it. I'm going to pick a number that seems strange, but it's actually not, as we'll see. But what is the probability? I'll use words this time. What is the probability of a z-score between plus minus 1.96? Okay. First thing that I would encourage you to do is start with, okay, z-scores follow a normal distribution centered on 0. That's a good place to start, right? And so you start by sketching it out. And tale as old as time, none of my students ever want to draw the curve, but eventually you'll start drawing the curve and realize, wow, that's a nice way to organize my thoughts. So it's a nice place to start. And I encourage you, even if it doesn't make sense right now, then just kind of keep drawing the curve when you're solving these problems so that you can try to visualize what you're trying to solve. And so here, this is centered on 0, right? And I want to know what love is. No. The probability, which is the area under the curve, between negative 1.96 and positive 1.96. What's really fun about these is, and also annoying, is there are lots of different ways that you can get to the same results because these are all just puzzle pieces, right? Take a block of 1 and chop it up, okay? But the areas don't behave the way you want them to because we've got this slope, right? And so we know how rectangles behave, but that's not how it's gonna work, right? And so we have to use the Z table to find these areas. It's snowing. Oh my gosh. So I want you to think about how you would naturally kind of try to problem solve this, right? This is our first one, basically. So, you know, set your expectations to be reasonable, but it's always good to kind of dissect how you think about these problems, because it's not necessarily the same way that I think about these problems. Yeah? And if you're completely lost, you can just use my way and it'll always work. But sometimes there are more elegant ways, but I try to pick the way that will kind of always work, brute force. And so when possible. So think about how you would solve it, right? And with practice, we'll get a lot better. But what's the area that we want? The probability is the area, right? The area that satisfies this condition. We want to have a z-score between these two values, making this the area that I want, right? I want to find that area. That's a good place to start, right? Because if I remember that the total area is 1, what if I what if I find this area, lob it off from 1, and take this area? I can do that. Lob it off from 1, and then I have the area I want, right? And so it's going to work like that, right? You'll be able to kind of cut pieces out that you don't want, right? Add pieces together if you want to do that. Yeah. What's another thing that I would start thinking about and leveraging? We'll see, but this is symmetric about 0. So if I have a negative 1.96 and a positive 1.96, do you expect this area to be the same as this area? Probably, right? Well, definitely. And so let's find the area to the left of negative 1.96 first. So this here, where's my table? Negative 1.96, I want to make sure I'm on my negative side. I really marked this up, didn't I? Negative 1.9, and then I'm going to go down from 6. I get a beautiful, well, I circled it. .0250. That's a nice clean cut, which is why I chose it. We can check on the positive side of 1.96, right? Z is positive 1.96. What if we go there? Positive 1.96. Hey, oh, wait, that's the area to the left, right? So always, it's always giving you the area to the left. And so now the area to the left of the point is 0.9750. So here, if you want, you can label it like this. 0.9750. Opportunity presents itself, right? I see. Now I know that this area all the way down is 0.9750. What if I, instead of lobbing off the tails from 1, what if I just lob off this 0.025? Then I'm left with the area I want. That's another option, right? And you would find that you would get 0.95, however way you slice and dice this thing. And so this area here is going to be 1 minus 0.9750, which is, I really hope yes, is the same as the other side by symmetry. So whether you take one, right, the total area, and you take off those sides that you don't want, or if you take the area to the left of the top one and lob off the area you don't want, either way, this probability is 0.95. So the probability that Z is between negative 1.96 and 1.96 is 0.9. Which is actually what we want to say. So when we use the 2, the plus minus 2 as a rough guide, really usually what we mean is 1.96. But 1.96, if we take a step back, is basically 2, yeah? And so, but we're going to talk about this 95 quite a bit. Okay. So Six Sigma, if you worked in industry, a lot of companies were embracing the lean Six Sigma process, but it's really just the fact that you have 3 standard deviations on either side of the mean before you're kind of, it stems from process control where you're kind of producing bad items if you're beyond Six Sigma. But anyways, oh yeah. I'm gonna make some notes here. So far, we have just started with a Z-score, right? And found probabilities associated with a Z-score. We have found probabilities associated with a Z or a Z-score using the Z table. We're going to get lots more practice, don't you worry, using the Z table. But usually if we think back to the SATs and the ACT scores, right, we don't have a Z distribution to start off with, right? And so what we do is from any distribution, so from any normal distribution, I'll use capital N. You don't have to. From any normal distribution, we can still find probabilities by standardizing our values first. By standardizing our values, potentially more than one values, first, which is going to look like this. If X, so SAT scores or ACT scores or whatever, follows a normal distribution with a mean of mu and a standard deviation of sigma, then you have some observed value that you're interested in, right? Finding the probability of some value. So what you're going to do is the next part, you're going to standardize it. So from this normal distribution, you're gonna standardize it and find Z. Okay. So standardize the value of interest, which is your X. And little x came from a population of big X, if you want to dive deep. Yeah. So now this X is going to just morph down onto the standard scale. Right? Then you'll be able to find the probabilities associated with Z or X, right? Because X has just been kind of shrunk down onto a standardized scale, right? And so the probability that you find associated with the Z is going to be the same probability for X, for Z or X. And this is using the Z table. Or software, bless you. No? I want you to try this question, and I am pushing you in the deep end, and it's going to be sink or swim. But we're going to start here, right, and pick up here. But try this question for Wednesday. Oh, that looks like a cruel smiley face. Should be a happy smiley face. Yay. But also a little bit cheeky. You can read it on your own, I trust. Try it. Have a great weekend. If you have any questions, let me know. Otherwise, I'll see you on Wednesday.